to get straight in your mind is that the big difference when we're looking at particles between physics and chemistry is that in physics, we're always interested in the nuclei. What's going on inside that nucleus? How are the protons and neutrons interacting? What do they want to do? We're not worried about the electrons around the edge that often. We talk about them sometimes, but normally only when they're picking off or flying into the nucleus. We rarely care what they're doing when they're just chilling in orbits. So most of the time, what we care about is what's going on inside that nucleus. And when we're thinking about decaying and radiation, it's purely what's going on inside that nucleus. Beta decay, that stream of electrons coming off stuff, doesn't come from the electrons around the outside. No, no, no. It comes from the nucleus. So, why do nuclei decay? Well, we talked a little bit about this last lesson. But basically, remember, there are two charges at war inside the nucleus. We've got electromagnetism, or charge, with all those protons, and they're pushing each other apart. They want to break up. But we've also got the strong nuclear force, which is attractive at 1 femtometer, remember? That's pulling everything together. And it is that tug of war between the charge wanting to pull stuff apart and the strong nuclear force wanting to bind stuff together that determines how stable a nucleus is. And the more unstable it is, the more likely it is to decay. There are 3 ways a nucleus can decay. The first is by far the simplest, and that is alpha decay. In alpha decay, we've got our massive nucleus, and it decides, I just want to be a bit small. So it ejects 2 protons and 2 neutrons out of it. And they fly out as a massive, heavy alpha particle. And we know that these alpha particles are very, very big, so they don't get very far, they're not very penetrative, but if they do hit into something, they do a lot of damage. So an example of an alpha emitter you could find in your home would be in a fire alarm, and it's perfectly safe because the skin will block the alpha radiation. However, if you were to swallow the alpha emitter, you will die horribly because then all these big, heavy, high-energy alpha particles will no longer have skin between it and your fleshy bits, and you will go down hard. So don't eat your fire alarm. So that's what's going on with alpha decay. Now we get on to what we call beta minus decay. Why minus? Well, because it's emitting electrons. We call them beta minus particles because they have a negative charge. Electrons, beta minus, simple as that. Beta just, it's another word for electron. So what's going on there? Well, inside the nucleus, something has changed. A neutron has changed into a proton. So one of these neutrons has changed into a proton. However, it can't just do that simple flip. And the reason for that is conservation laws. Now we've already met one conservation law, and that is the conservation of mass and energy. They're not independently conserved, but we know they're the same thing, E equals mc squared. We can go from mass to energy and energy from mass. And that whole stuff, that mass-energy equivalent, is always the same amount in the universe. If you were to measure all the total mass and energy and you were to work that out, that number's going to stay constant all the time. It's never going to go up, it's never going to go down. That is constant throughout the universe. Well, we're going to learn in quantum mechanics that lots of other things are also constant throughout the universe. They never change. And one of those is charge. The total amount of charge in the universe never changes, always remains the same. So when a neutron turns into a proton, well, we've had no charge here, now we've got a positive charge. So in order for the universe to stay in sync, we also need to spit out an electron, because then our charge before is 0, and our charge afterwards will also be 0. Now, anti-electron neutrino. Don't worry about this. We'll get to this in a separate lesson. This is for a different conservation law that you do need to know, but I don't want to focus on today. So this is our beta minus decay. Inside the atom, a neutron's flipped to a proton, and it's going to spit out an electron. The electron's going to go flying out of that nucleus. Does this to become more stable. You're also going to get this anti-electron neutrino thing flying out. Again, don't worry about that today. So this is our beta minus decay. The other sort of decay is beta plus. That is where a proton turns into a neutron. So again, one of those nucleons inside the nucleus, one of those protons or neutrons decided, I'm fed up being this, I'm going to try out, I'm going to move to the other side. So the proton turns into a neutron. However, again, we need to make sure the charge remains the same, because charge is always conserved. So it's going to split out a positive electron, and also a silly neutrino. Positive electron, well, it has to spit out something, because we've got positive charge before the negative charge, so we need something to make the charge work. What is a positive electron? Well, a positive electron is something called positron. And it is antimatter, a different form of matter that works differently to normal matter. And we'll learn all about that in the next lesson. You need to know these three forms of decay at a very, very basic level, what's going on. Alpha decay, something spitting out. Beta minus decay, which is where we get our beta radiation from. A neutron's turning into a proton and an electron, and this silly neutrino. And beta plus decay, a proton's turning into a neutron and this strange positron, and a neutrino as well. What the positron is, and the neutrino is, well, we'll have to wait 2 more lessons to find both of those out. But I just wanted to make sure everyone was happy with what was going on when we talk about what's going on inside the nucleus. Bits are either coming off the nucleus, neutrons changing to protons, protons changing to neutrons. That's what's going on when nuclei decay. There'll be more lessons throughout the week to fill in these gaps. Keep on trucking.